Seismic slope stability is about either computing a factor of safety under some kind of seismic loading condition and making sure that factor of safety is high enough, or computing a displacement and figuring out if that slope displacement is tolerable. So for example, here's a slope. What we will often do is, before we would have the weight of the slope in a static problem. Now we add a horizontal body force. That's a static body force. Of course, in real life, acceleration changes, right? It's a time series. And so in reality, the acceleration of the slope will be time variable, but we often will simplify it as being this constant kh multiplied by the weight of the sliding mass, W. Um, the shaking that happens during an earthquake has two main effects. First, it increases the shear stress, right? You can imagine if this mass is, accelerating, there would be a resultant force that would push the slope downhill, and that resultant force will increase shear stress acting on the sliding surface and therefore make the slope more likely to move as a result. It has another effect too, which we won't talk about the other effect in this video. That'll be saved for another video, but it will decrease the shear strength too. So due to things like liquefaction, buildup of excess pore pressure, even if it doesn't fully liquefy, the soil may get weaker. There's cyclic softening of clay-like soils where cyclic loading will make it weaker, softer. And there's also mobilization of residual shear strength for sedimentary rock formations where the earthquake might actually cause the rock to move a bit, and that movement then will move the soil more toward a residual condition and make it weaker and more likely to slide again in the future. So the different approaches I mentioned already. First, you could design for a prescribed seismic demand and some factor of safety. So a common one might be like you have to plug in kh equals 0.2, and if your factor of safety is 1.1, you're good. If it's less than 1.1, you have to do some mitigation, make the slope stronger, make it flatter, do something to make its factor of safety go up. This kh value depends on seismic hazard. If you're in a highly seismic zone, it may be pretty big, like maybe as high as 0.4. It's generally less than PGA, so if you do a sort of building code level design for 2,475-year return period ground motion, kh is going to be less because there's some averaging over the thickness of the sliding mass. And then the factor of safety is also reduced, so we don't plug a 1.5 in there for factor of safety because earthquakes are already rare events. The factor of safety, in a way, is getting at probability of failure. So if you have a rare event, you can use a lower factor of safety than if you have just static equilibrium, where we would use a factor of safety generally of 1.5. One problem with this procedure is that designing slopes to meet this target factor of safety, especially in high seismic regions like here in Los Angeles, it's often infeasible. Like you just can't get a factor of safety of 1.5 or of 1.1, even with a kh as low as 0.2. And so, we often will look at, well, okay, we can't get this factor of safety requirement. What else can we do? Because it's quite possible that you could, you could not get a high factor of safety for a pseudostatic horizontal body force, but because you only exceed that a few times for a few cycles, the slope might not move very much. And you might say, oh, it's okay if the slope moves a little bit, I can live with that. So let's look at these displacement-based design methods. So in that case, you can actually allow the factor of safety to go below 1 if the displacements are tolerable, right? How much displacement is there going to be? If it's going to be like 30 meters of displacement, that's probably not tolerable. If it's going to be a centimeter, that's practically zero. It's not even clear that anybody would notice a centimeter of movement after an earthquake. So what we do is typically estimate using a Numark sliding block method, and that Numark sliding block method can be run on a time series itself. So you can plug in a time series and a yield acceleration, or more likely you would use equations where other people have done many of these Numark type analyses, not always with a rigid block, and develop equations that are regressed to those simulations. Or another option is you could run your own numerical simulation, right? You could do a nonlinear time series analysis, put ground motions in the bottom, and figure out how much deformation there's going to be. That especially is attractive if none of the existing equations match your particular problem all that well. And the tolerable amount of displacement really depends on land use, consequences. You know, are there a bunch of houses up on top of this slope or below the slope where movement of the slope might have a big impact? Or is there, maybe there's just a roadway that goes through and you can go and quickly repair it as long as the deformations aren't too big. So it really kind of depends on the problem and needs to be coordinated in, you know, with the client to come up with a tolerable amount of risk for that displacement. So let's go through the steps for the displacement-based design. Okay, the first step is really kind of like the main focus of this class being a slope stability class. The other steps might be more for an earthquake engineering class. But you would first perform a limit equilibrium analysis with some horizontal body force. So you would put in a value of KH and run the analysis, and it will give you a factor of safety. That factor of safety will be smaller than if you have KH equals 0, just for static loading. And then you would iterate on that KH value until you get a factor of safety of 1. That means when the horizontal body force is equal to this value of KH, we have reached a yield condition, so I'm going to call that the yield acceleration or the yield coefficient K sub y. All right, then we know Ky and we know how much the actual demand is, right? So now we have to estimate Kh for design. This is usually 0.05 to 0.4 typically, depends on seismicity and the importance of the slope. Here in LA, we might tend more toward these higher numbers, being near highly seismic, faults. Okay, if Kh is less than Ky, then small displacements should be anticipated. What this means is that the demand is less than the capacity. And you might be thinking, why would we not just expect no displacement in that case? Well, the reason is that limit equilibrium assumes the soil is rigid and then perfectly plastic. In reality, soil has some kind of nonlinear deformation behavior, right? So it's possible to get some deformations before you reach a failure condition. Typically, Kh will be greater than Ky, and in that case, some displacement should be expected. And the displacement depends on a few things, like how big is Ky over Kmax, right? If that becomes a small number, that means Kmax is now your maximum demand. Ky is the yield acceleration. If this number is small, it means that the demand is significantly higher than the capacity. It also depends on the shaking characteristics of the slope. Okay, slopes are compliant bodies that can deform, and they have maybe their own natural frequencies. It depends on the ground motion characteristics, right? Does the frequency content of the ground motion align with the natural frequency of the mass? If so, you'd get a lot of amplification. It also depends on duration. You know, a long duration motion is going to induce more displacement than a short duration one for a given peak intensity. And it depends on frequency content for reasons I'll show when we get into Numark's sliding block. All right, so the Numark sliding block method is a simplified representation of a compliant slope body. So here we have the real slope. Maybe it's actually 3D, right? This is a 2D slice through it, and you have some acceleration going on here and a sliding mass right there. We're not going to analyze that entire thing when we do a Numark sliding block analysis. What we'll do instead is figure out the yield acceleration, and then we'll model it as a block on an inclined surface. And the yield acceleration would be related to the slope of that inclined surface and the coefficient of friction between the block and the surface. And notice that technically a slope might yield in the other direction if the shaking intensity is high enough, just like the block might move uphill. Oftentimes the uphill movement is neglected when we do this sliding block analysis. So the idea now is that if we have an acceleration time history, so we're coming along and you've got a few big cycles of movement. This doesn't particularly look like a real acceleration time series, but it'll get the point across. And if we had our yield acceleration here, right, this is Ky, well then we have, in this case, 2 cycles that have exceeded the yield acceleration, and we would expect some displacement to accumulate during those cycles. The amount of displacement is really going to depend on the area of the acceleration time series that's above the curve. And in this case, I'm ignoring the other direction, so we're not getting any kind of acceleration the other way. So that's acceleration. Let's look now at relative velocity. So what I'm talking about is in the context of this Numark sliding block, what is the velocity of the block compared to the velocity of the sliding surface underneath the block? And so those two things will be exactly the same until there's slip, right? And so once there's slip, that you'll start to get some relative velocity. So the first slip should happen right at this time, and you will get some kind of positive relative velocity. And then once you reach this point right here, that positive velocity doesn't necessarily stop. It may just kind of change direction and come back down like this. And then here's one, and maybe the block is now slowing down, and maybe it yields again before it reaches that point and comes up to this point right here, and then slows down again. So you might get something like that happening, right, in terms of relative velocity, and then they're stuck back together for the rest of the motion. All right, so we can further integrate now. These relative velocities are basically the integral of that area, and then there's some slowdown phase that comes after the acceleration has gone back down below ky. So if you were to come in and do relative displacement, it's going to go up like this, then maybe up again, and you would get some final amount of relative displacement. It's not a very good straight line. Here we go. And this is now the Numark displacement. Okay, that doesn't mean that the slope is actually going to deform that much, right? There's elastoplastic deformations that can happen. We're simplifying this as a rigid body, but it's kind of an index. It'll tell us if this is 10 meters, that's going to be a lot of displacement. If it's a centimeter, the slope's not really going to move very much. And so we can think of it like that. So some of the original work done on this was by McDeasy and Seed back in 1978. And they were studying the deformation potential of embankment dams. And they ran some finite element simulations. These were not nonlinear finite element simulations, but equivalent linear, just to get the shaking demand throughout the embankment to model the dynamic response of the embankment. And then they would couple that with kind of a Numark procedure. So you calculate ky, the yield acceleration, they performed equivalent linear finite element models to obtain demands, and the heights of the dams were 23 meters to 46 meters, and then used the Numark method to compute displacement. And the input acceleration was either the maximum value at the crest or the depth averaged acceleration time series. And they kind of bounded the possible range of displacements that way. Then they did some regression to relate the ratio ky over kmax to this dimensionless quantity u over kmax t naught, where t naught is the first mode period of the embankment, kmax is the maximum acceleration, either the maximum acceleration of the crest or the maximum average acceleration, and u is displacement. And they have these figures here that show that for a given ky over kmax ratio, you're going to get more displacement for a large magnitude event than for a smaller magnitude event due to the larger number of cycles and lower frequency content, therefore longer excursions above ky. All right, then there's been more recent work done. So Bray and Travasaru, 2007, and there's even a family of methods that are newer than this. They did a little bit more sophisticated analysis with a much larger number of ground motions. So they have a fully coupled stick-slip model. So instead, here's the slope. What they do is represent it as a compliant mass that's it's like a flexible sliding block, so that the natural period of the sliding mass is the same as the natural period of the slope. And that way you're modeling the dynamics and the amplification or de-amplification of shaking through the embankment. They used 688 ground motions, all from shallow crustal events. These were from the NGA West project, I believe. And they varied the natural period of the slope, the yield acceleration, and the ground motions, and computed these displacements for about 50,000 total cases. So really a lot of work went into doing this. And these are plots of some of the residuals. So this would be like the displacement. So first they computed displacements from the nonlinear stick-slip analysis, and then they did regressions and came up with equations that simplify that so that users don't have to come along and rerun their stick-slip model. They can use these simplified equations instead. So these residuals are the difference between the displacement that was computed from the nonlinear stick-slip model minus the displacement that was predicted by their equation, and then their natural log space. It's the natural logs of the difference, the difference of the natural logs. So you can see these residuals are pretty big, residuals of 3 or higher. So there's quite a bit of scatter, just because it's hard to capture a single nonlinear time history analysis with some simplified parameters. But you can see overall it's unbiased with respect to magnitude, quite a bit of scatter, but no trend there. Unbiased with respect to the yield coefficient, the natural period of the slope, and also distance. And so these are the equations. An important contribution here is that there's some probability of having zero displacement. And zero means smaller than 1 centimeter in the context of this analysis. So if you're doing a probabilistic analysis, you can quantify that probability. And then they have a separate equation for the conditional displacement. So given that there is some displacement, this is the mean value of that displacement. Well, there's an error term at the end, so the part before the error term is the mean value. And this equation on top, equation number 5, is for a compliant slope that has some natural period Ts. And the equation down here is for a rigid block, or for a very short slope, or something with a natural period that's very low. All right, now I mentioned there have been other ones. So Bray et al. 2017 did a similar exercise, but for subduction ground motions, using even more than 688. So these are not shallow crustal events; these are big subduction events. And then Bray and Macedo performed an update of the Bray and Travesaru for shallow crustal motions, but again ran many more ground motions. So an important point with these models is that the error term, that epsilon, really quantifies the difference between one kind of analysis, which is a nonlinear stick-slip analysis, and these simplified equations. It's not an overall quantification of all of the error, right? Because the stick-slip model might not match perfectly the reality at a particular site either. Although they did show that their approach agrees reasonably well with measured slope displacements. So this epsilon is really a modeling error term, not an overall error term. Then there's this tool called Slammer. This is a USGS product by Gibson, Ratji, Gibson, and Lee. And so you can go and check out this Slammer tool. It has methods for computing slope displacements. It has ground motions from the peer database, and so it's a nice tool too for doing these sorts of simulations.